Assalamu alaikum everyone. In this lecture, we are going to discuss about our experiment number 3, which is application of bipolar junction transistor as amplifier and also as switch. So let's start. The first question we might ask is what is BJT, and I think this thing has already been covered in your theory lecture quite a bit, so you already know what is BJT. So BJT stands for bipolar junction transistor. This is a semiconductor device. In general, there are two types of transistors. One is this BJT and another one is FET or field effect transistors. Now, I think you already know that this kind of transistors, BJT has three terminals, emitter, base, and collector. And there are two particular types of BJT. Here we can see one of them is NPN and another one is PNP, right? So why is it called NPN? Because there are three types of semiconductor. Here N, this is P-type semiconductor, sorry, P-type semiconductor, and the last one is N. So the particular configuration here used is such that in the middle we have P-type semiconductor, and in the both side we have N-type. That's why it's called NPN. And there are another type which is PNP, where P-type semiconductors are at the outside, right? So also you can see the general symbol that we can use for NPN and also PNP. And in our experiment today, we are just going to use the NPN type transistors. So we are not going to discuss that much about PNP. And to understand how our BJT or bipolar junction transistor works, a simple analogy that can be given here is this one. So you can see this water tap can be thought of as a transistor, right? This knob here, which controls the flow of water, can be thought as our base. And as you can see, water is coming from here and water is going out to there, right? And in the same way, our base is controlling the current flow in our transistor. So current will flow from collector to emitter, but that will be controlled by our base. That's the general idea of our bipolar junction transistor. And a very important question that can be asked is why there is a bipolar in this name, bipolar junction transistor. So I'm not going to answer this question right now. You have to find it yourselves, and I might ask this question in your class, so keep it in mind. So yeah, in this experiment, we are just going to implement these two types of application. One of them is amplification and another one is switching. So let's go there. And before we start our experiment or theory about that, we need to identify the pins of a practical transistor or BJT. So we already know that there should be three terminals or pin in a particular BJT. So here, as you can see, this one is a example of a practical transistor, and this one is NPN type. The model number is BC547, which we are going to use in our lab for experiments. So you see the whole device looks kind of rounded at the bottom, but at the top there's a flat surface, right? If you face this front part, the flat part, to yourself, then the left pin, the left one should be our collector, the middle one should be our base, and the last one, the right one, should be emitter. In this way, we are going to find out our three pins: collector, then base, and then finally emitter. And this is only true for our NPN type of transistor. And the transistor that we are using here, BC547, is an example of NPN transistor. But what will happen if the transistor is a PNP type? Then it will be exactly other way around. That means previously for NPN, the left one was collector, For PNP, left one will be emitter. Base will be same as this is in the middle, but for the right one it will be collector in this way. So for PNP like this. So we are just going to use this uh, convention here because we are using the NPN type transistor. So let's move on to the next slide. So now, before we try to implement the circuit for amplification and also switching, we need to understand another thing, which is modes of operation. Okay, so what is modes of operation? For a particular transistor or BJT, there can be three modes of operation based on the values or voltage we are giving at the base or collector or emitter, right? So what are those? As you can see, there are three terminals and three semiconductor uh, materials here like this. So as I have said before, all the examples I'll be giving will be of NPN transistor. So this is an example of an NPN transistor. So the material should be like this, NPN, right? So this is our base. The top one is collector, the bottom one is emitter. Then, so there, that means there should be two junctions. One of them is this one. This can be called as EBJ or emitter to base junction, and another one is this one, which can be called as CBJ or collector to base junction. Now we know that each of these junction can be either forward biased or reverse biased, and based on the situation here for this junction we can have three modes. If both of these junction, that means CBJ and EBJ, both are reverse biased, at that moment we can say it's in cutoff mode. For the second mode, both of them should be in forward biased like this here, so that will be called saturation mode, and both of these modes will be used in our switching applications. You need to remember this. Then the third one, which is in that case the emitter to base junction, this one should be forward biased, but not the other one, which is collector to base junction, that should be reverse biased. In that case we are going to name it active mode, and the amplification application will be used by this mode. Okay, then another thing that needs to be discussed is the general convention of naming. So here you can see that the current that is going through our emitter can be called IE, the current going through our base is IB, and the collector current is IC, right? You already know those, I think. And the voltage that we are going to get across our base and emitter, this one can be called as VBE. And another one very important is this one. So the voltage between the collector terminal and also emitter terminal, these two difference of voltage between these two terminals can be called as VCE, and the other one, which is the voltage difference between the base and the collector, can be called as VBC. So now I think we can move on to our next slide, which is to understand how to use BJT as switch. And at the left you can see this circuit where we have implemented BJT as switch. So how we can use BJT as switch? From previous slide we already know the requirements are we need to operate this in two modes. One of them is cutoff and another one is saturation. And based on those mode, as we can see at the right, there will be two possibilities. In one, we will see that our BJT is totally turned off, or this collector to emitter path is off. That's why this is open circuited, and that's why there will be no current flow through our load RC. So no current will be flowing through this branch. That's why this is off condition. And in the next condition, if I give a different kind of voltage at our base, there will be a possibility like the path from collector to emitter, that will be short circuited. That means the voltage that we can say VCE, the voltage between collector to emitter, that will be almost close to 0 volt. That's why this is shown as short circuited. At that moment, a good amount of current will flow through our resistor RC. Uh, so that can be thought as our on condition. So there are two conditions, off and on. That's why we are calling this as switch, because so we can turn on or off using our controls parameter, which is VBB. So let's now go into a little bit more detail how that actually works. So in this circuit, if we look at the lab sheet, we will see that VCC is given as plus 12 volt. Then VBB can be two different values, either can be 0 volt or 5 volt, right? Then the particular values for these resistors, RC is equal to 4.7k, RB is equal to 10k, and there is also another thing here, which is the LED, just to verify that our circuit is properly turning on or off. That means whenever our LED is turning on, we know that our circuit is turned on, and in the other case it's turned off, right? So that's why there's an LED. Okay, now how it actually works, whenever you give this 0 volt here at the base, no current will flow through there, so IB is equal to 0, and as a result we know our emitter terminal is grounded and VBB is also grounded, as we are giving 0 volt. So this junction, emitter to base junction, is actually reverse biased, and as we already giving 0 volt at the VBB, this is a positive volt, we know this should be also, the collector to base junction should also be reverse biased. So both of these junctions are reverse biased, which fulfills our cutoff mode condition. That's why we are in cutoff mode. And uh, we are going to tabulating some values here for VBB is equal to 0 volt. So as VBB is equal to 0 volt, our current IB, base current, should be 0. Our current through the collector branch here should also be 0. As we know, right now it's in cutoff mode, our whole thing is turned off, so this is 0 ampere. Then what should be the value of VCE? That is the value from here to here, right? So this is called VCE, the voltage across collector to emitter terminal. So what should be that? As our whole transistor is turned off, no current should be flowing through here, no current should be flowing through our RC resistor. That's why whatever value that is available at the VCC should be directly coming through here. So we can say VCC is equal to plus VCC or plus 12 volt for our case, right? And then for the next case, we are going to be giving a voltage plus 5 volt at the VBB, and already VCC is plus 12 volt as before. RC, RV, every value will be just like before. Then what will happen? At that moment, what will happen is that because we are giving a positive voltage at VBB, at this base terminal here, we are going to be getting a positive voltage which is 0.7 volt higher than our emitter node here. That's why this particular junction, emitter to base junction, will be forward biased, and because of this VBB, there will be some current IB, right? The base current, and we already know a simple equation which is IC equal to beta IB, right? So beta is an amplification factor. The basic purpose of, or basic ability of our BJT device is that whenever we give some kind of current, at the base terminal here called IB, it will be amplified by a amplification factor beta, which is typically around 100 to 1000. So that means if I give some kind of current IB at the base, obviously that will be amplified by some factor, and that value will be coming through our collector branch here as collector current. Okay, so there will be some current at the collector branch IC. Because of that, there will be some voltage drop ICRC, right? And because of this voltage drop, the voltage here will be lower than before. And typically, as our VBB is very high, we will see that the voltage has dropped to around zero point 0.1 to zero point 0.2 volt, okay, which is our VCE. Theoretically, it can be thought as almost 0 volt, but practically we will see that there will be some voltage across our collector to emitter um, terminal. So that's why you will see that right now our BJT is turning on. There will be some current IC, there will be some current flow through our RC, and our BJT is performing as on condition. Okay, so what will be the value for switch on condition when VBB is equal to 5 volt? Obviously, IB will have some value which you will find out in your lab implementation. IC should also be found out by you by measurement, and VC should be around 0.1 to zero point 0.2 volt. So you have to measure that also and verify. Okay, so that's everything about BJT as switch. But why we are finding all those values like IB, IC, VC for each of this condition when switch is off and also when switch is on? Why are we doing that? To understand that, we have to understand what is DC load line in BJT. So I think you have already seen this kind of graph, the IC versus VC graph for BJT previously in your theory lecture. So this particular graph actually comes from these equations. So IC is equal to IS e to the power VB by VT. So this particular graph actually gives us an understanding or characteristics of the particular transistor that we're working. So transistor can be characterized by this graph here, and you can see there is not only one line, there are several lines here corresponding to several values of IB here. So what that actually means is, as you can see in this equation, based on different values of IB, there can be different values of IC. So that's why there, based on the values of different IBs, we are going to get different lines here. So IB0 here denoting the value which is almost close to 0 ampere, okay, and maybe IB1 can be 5 microampere, something like that. IB2 can be 10 microampere. So as our base voltage is increasing, our graph will be shifting up. That's why there are several graphs. There can be more graphs here if we want to, like this. So we are just showing some particular graphs for some particular values here. I think you understand that. Okay, then, so what is DC load line in BJT? To understand that, you see, previously this graph here at the left was showing the characteristics of our particular BJT here. But when we are using that BJT in a particular circuit like this one, with some values of RC, RB, VCC and everything, when we are implementing that in a circuit, then that particular circuit can also be described by one equation, right? So using our simple Kirchhoff's voltage or current law, we can find those uh, characteristics. Like here, if I just implement or apply Kirchhoff's voltage law for this branch here, we are going to get this equation, VC equal to VCC minus ICRC. So This equation and the previous equation actually governs our whole circuit, right? What I'm trying to mean is that these particular purple graphs are actually showing the characteristics of this particular BJT, which is inherent in this device. To show the characteristics of this circuit here, we are using this equation, right? And this equation can also be drawn here because there is VCE and also IC. So this can be drawn here as a line. This is a linear equation. So how to draw that? Theoretically, if I want to draw that, what I need to do is very simple idea is that we can just put VCE equals to 0. Then what will happen? We are going to get IC is equal to VCC by RC, right? So that means we are going to get one data point where VCE is equal to 0 and IC is equal to VCC by RC. For another case, we can put IC is equal to 0 in this equation, then find out the value of VCE. What will happen? At that moment, VCE will be equal to VCC. So another point is IC is equal to 0, VCE is equal to VCC. So these 2 points can be plotted in this graph here to get the linear equation or the line we are trying to find out. So let's take VCC here arbitrarily. So this is VCC, a value of VCE. So if I just want to plot this particular point here, IC is equal to 0, VCC is equal to VCE. So this one is that point, right? Because at this point our VCE value is VCC and Y value or IC value is 0. And the second point should be this one. To plot that, VCE should be 0 and let's say IC is equal to VCC by RC, maybe this point arbitrarily. Okay, so that is our point 0 comma VCC by RC. So these 2 points can be connected together like this. It should be straight line. I can draw very nicely like that, but you get the idea. So this straight line here is the DC load line of our circuit here. Okay, and you see we have got one line here corresponding to our circuit and another one, the purple graphs here, for the characteristics of our BJT. Both of these together will constitute the total characteristics of our system. That means if I say right now the value of IB here is equal to IB3, so this one, so right now this purple graph is active for the characteristics of our BJT, and another one is this curve is representing our characteristics of circuit. So the intersection point of these two will be constituting the value of IC and also VCE at that particular moment for this circuit. So in this way we can show the characteristics or the values of IC and VCE for a particular circuit. That is the significance of DC load line in BJT. Okay, so now, so practically you have to find out that DC load line. That's why we were finding out those values, right? For switch on and switch off mode, we are going to find out those values. Now what will happen? We have seen that in theoretical situation we were going to get something like that. So here and here this point is VCC and this point is VCC by RC, right? So theoretically, we were going to get a straight line like this one, but as we will see that in practical case, our VC is never fully zero. There will be some value here. VC is around zero point 0.1 to zero point 0.2 volt. Okay, so that's why there's a gap here, and that's why we are going to get this point here in our practical implementation. So there will be some VCE value, so we are going to get this point for on condition when we are giving base voltage as 5 volt, and for cutoff situation, theoretically we should get collector current as low as 0, but there might be some values, that's why we are going to get this value, not exactly 0, but that can be also 0, almost 0, very negligible amount of current that you cannot even measure. Okay, so that's why you are going to get these two practical points for these two conditions on and off, and you are going to find those out and plot these values to get the DC load line. So that's our task 1. So you have to just find out this straight line here, which is DC load line of our circuit. So now how to use BJT as an amplifier. This particular circuit that we can see here is actually designed for the purpose of amplification. So what is amplification? We know if we give some voltage at the base here like this one, and AC voltage obviously, then these voltage should be amplified at the output, which is the across our collector to ground here. And this kind of amplifier circuit is called common emitter uh, amplifier, because you see this portion here, this is the emitter junction, right, connected to emitter junction. This emitter terminal is actually common to both our input and output, that's why it's called common emitter. And to complete our circuit, we need to give the supply here, which is plus 15 volt according to your lab sheet, and there there should be a ground, so that's it. And also according to your lab sheet, there should be some value of R1, R3, R2 and R4. I'm not going to write all those things, you can find those values in your lab sheet. But yeah, we need to understand some of the things here, like why these 4 resistors are used, and also these 2 capacitors, that will be discussed here in brief. Okay, so I think you already know what is the purpose of biasing, why do we do biasing in our transistor for amplification. So the base idea is that we need to find a desired Q point, a operating point, so that our input can be amplified without any chopping off. So what is chopping off? Let's discuss that. So this particular graph is already known to you. So let's say for our circuit here, particularly we are giving a base voltage, sorry, base current as IB here, IB3 here, and so this graph is active, and this is our DC load line. So that means this is our operating point, right? The Q point. So how the amplification will be done can be visualized like this. So let's say we are giving a small AC signal at the input. So this should be like this. Okay. So you can thought this as our IB current. Maybe this is IB max plus, and this is our minus IB max. Okay. So then because of this input current, obviously we are going to get some amplification at the output, which can be visualized using our current IC. To show that, we can just uh, show it like this one. So here, because of this amplification, we are going to get um, a sine wave like this, let's say. Okay, this is our IC. But what will happen if you say our Q point is right here? Okay, this is, let's say this is our Q point. Then what will happen? Then our input signal should be looking like this one, which is IB. And because of this one, we are going to get an output current IC, which should be looking like this one, right? But because there is this zero crossing here, this portion will be chopped off. Okay, so like this. Let me draw again. So something like this will happen. So because of this Q point, we are not seeing some portion of our output signal which is chopped off. That's why we need a proper Q point, so that both the positive portion and negative portion of our output can be properly shown. So in our lab sheet, obviously these values of R1, R3, R2 and R4 are taken such that we get a proper Q point, so that we get a proper output. Okay, now let me explain the task that we have to accomplish. At the input, we have to supply a voltage of 100 millivolt according to our lab sheet, 100 millivolt sine wave with 100 hertz frequency. Okay, and then we have to measure the output here, and we are just going to get the AC signals at the output because of these capacitors here. These capacitors are called coupling capacitor. Whenever we use coupling capacitor, then all DC values are blocked, only AC values are permitted. So because of the biasing, we already know there should be some voltage VDC here, but this will not be permitted, only the AC values will be permitted. So the total value here will be VDC plus VAC. AC because of this signal amplification, DC because of this biasing. So total value is available here, but this coupling capacitor will only pass the AC values, because a particular capacitor acts as open circuit to DC signals, DC voltages. So that's why no DC voltages will be seen at the output here. Okay, only AC signals, that means the amplification of 100 millivolt will be seen at the output. And same thing can be said for this C1 capacitor. This is also a coupling capacitor, and we know because of the biasing here, because of the 15 volt, obviously there will be some voltages at this node here, and this cannot pass through this capacitor, so that no interference of input is happening. Okay, so yeah, that's it. So our task is to give 100 millivolt sine wave with 100 hertz, then measure the output. Then what we have to do is we have to find out the amplification we are getting. Let's say we are getting 10 volt at the output. Just assume, let's say we are getting V out as 10 volt. Our input was 100 millivolt. Then our amplification will be 10 by 100 millivolt, 10 volt by 100 millivolt, right? Which should be, I think, 100. So in this way we will get the amplification factor. And then another important thing is to find out the frequency response. What do I mean by frequency response? For any particular BJT and particular circuit, obviously for different input frequency, the gain at the output will be different. Okay, for 100 hertz right now. I have said that maybe we are getting 100 uh, sorry yeah, 100 amp gain. So whenever we are giving 100 millivolt, we are getting 10 volt at the output. So it is not true for all the frequencies. After we change the frequency to a different value, let's say 10 kilohertz, maybe the output will be different. This is because of the characteristics of the BJT and also because of the capacitors we are using, because the response at the output will be different, or the input uh, uh, and output impedance of this C1 and C2 will be different based on the frequency, right? Because we know um, capacitor impedance can be written as 1 by 2 pi fc, right? So this is the impedance, can be thought as our uh, resistance like behavior of our capacitor. So whenever we change the frequency here, obviously this impedance will be different. So obviously the response here, the voltage drop here will be very different for each particular um, frequency of input. That's why we are going to get different behavior at the output. So here you can see that you can give 10 millivolt or 100 millivolt, whatever value you give as input here. So just keep that fixed. Then start with 100 hertz, get the output V naught, and then change the frequency to a different value. Take 4 or 5 different data points here, let's say like 100 hertz for maybe 500 hertz, then maybe 1 kilohertz. Like this you take different values, input voltage is same, then check the amplitude of the output voltage, and based on the input and output value, obviously you are going to get a gain value. uh, put those here, and we know that gain in decibel is equal to 20 log A is our gain. So you can also write those values here also. So that's your task, to find the frequency response of our amplification circuit. So how it behaves with respect to the change in frequency in input. That's it for this lecture. Allah Hafiz.